videos, we've discussed many different techniques for proving statements. We could go on and on and on about different proof styles. We haven't even mentioned induction or combinatorial proofs here, but instead we will end with one final useful technique, proof by cases. The idea is to prove that P is true by proving that some Q implies P and not Q implies P for some statement Q. So no matter what, whether or not Q is true, we know that P is true. In fact, we could generalize this. Suppose we wanted to prove P. We know that at least, real quick, let's say we know that at least one of Q1 or Q2 or Q3, at least one of these statements is true, and we know that this all implies that P is true. If one of these is true, no matter what, if this is always going to be true, no matter what, then P must be true. So if we can show that Q1 implies P and Q2 implies P, all the way up to Qn implies P, then we can conclude that P is true. The key thing is that we want to be sure that one of our cases, the Qi's here, must be true no matter what. So if that's confusing, perhaps an example will make things better. Let's prove that for any integer n, the number n cubed minus n is even. And I promise after this example, you'll understand what proof by cases really means. So it's hard to know where to start this because we don't know much of anything about n. We might be able to prove that n cubed minus n is even if we knew that n was even. In fact, we could probably prove that n cubed minus n was even if n was odd. But since n must either be even or odd, this should be enough. So here's the proof. Here's what we're going to do. We're going to consider two cases. So first, we're going to look at if n is odd. Actually, first we're going to look up even, although it doesn't really matter. So case one, n is even. So then that means that n equals 2k for k being some integer here. So this means that n cubed minus n is just 2k cubed minus 2k, which is 8k cubed minus 2k. But here's the important thing. We can factor out a 2 to make it 4k cubed minus k. This is 2 times an integer, so then n cubed minus n is even. Okay, so we showed that this is even if n is even, but we're just making assumptions about this n here. We don't know that n is even. N could be odd. That's the only other option for n. So let's look at case 2 now. Case 2 is n is odd. So then n equals 2k plus 1 for some integer k. So then that means that n cubed minus n is 2k plus 1 cubed minus 2k plus 1. The algebra here is a little bit tricky, so this is going to be 4k squared plus 4k plus 1 times 2k plus 1 minus 2k minus 1. I'm just doing some algebra and some simplification here. So this is 8k cubed plus 4k squared plus 8k squared plus 4k plus 2k plus 1 minus 2k minus 1. And I guess we can drop the parentheses here at this point. Now, I'm not going to simplify the algebra anymore because I can show at this point that, this 1 and that minus 1 cancel, and that's all I need to show because now I can factor out a 2. This is, let me make that a little bit smaller. This is 2 times 4k cubed plus 2k squared plus 4k squared plus 2k plus k minus k. The important part is I factored out that 2, so n cubed minus n is even. It's 2 times an integer. And so since 4k cubed plus 2k squared plus 4k squared plus 2k plus k minus k is an integer, n cubed minus n must be even again. It's even. Either way, it's even. N cubed minus n is even, whether n is even or n is odd. But doing this strategy made it easier, and it allowed us to have more tools underneath our belt to be able to prove that n cubed minus n was even, regardless of whether or not n was even or n was odd. Anyways, that's how to prove by cases. Thanks everyone, and I'll see you in the next lecture.